All right, good afternoon. Let's start the class. Okay. Yeah. As the midterm is being circulated, just be patient. There's no rush. Okay. Yeah. And make sure you put them back into the slots. Huh? Yeah. Anyway, the midterm for this section, the average is 62%. That's not as good as I have expected. So I did a little bit statistic analysis, very basic one. So I counted. Did somebody?
From last class.
Oh, maybe he's calling.
Find my iPhone.
Do you know how to turn it off?
You break it.
Okay, hopefully it's not going to go. Anyway, so the class average is 62%. The number of students below 50, there are 40 students. And the number of students above 80, and there are 40 students. So, see, there are two big humps here, right? Yeah. And so I have no question about the students above 80%, so let's keep doing what you're doing. But for those who are below 50, okay, and then they have a serious concern, especially for some of them who are below 20. So you need to make a serious plan for the final exam. Okay, as you probably noticed, the final exam is on December 5th, which is probably the first one of your second year's final exam, and that's pretty much right away after our last lecture, right? That will be a challenge because final exam covers a lot more material, and now you have much less time to prepare. Okay, so the challenge for the final exam, not because the question going to be a lot more harder, but because that all the other factors together, then you might not even have time to get ready for it, right? So make a really early a plan for the final exam if you're having trouble, okay, from midterm. So look at the trouble you have, huh? Yeah, I will talk about a little bit about the trouble. A lot of the trouble that you have actually relate to your first year calculus. Okay? So derivatives, integrals, and a lot of it related to the way that I think I pointed out sometime in the lecture, the way that you write mathematical expression, and you actually confuse yourself. And some of the trig identity, some people just come up with a trig identity themselves, which actually doesn't exist, right? So take a look at it. I'm not going to go over in detail in the class, but I'll be more than waiting to go over the midterm with you guys if you want to come to my office. Okay, one-on-one, that's fine. Okay. So the point is, don't just discard it and that's it, right? We need to learn a lesson from it to make sure we make a good plan for the final exam. Okay. So I know the other section actually slightly higher than this section right here. Better call this number, I guess. So anyway, oh, what was it? Yeah, the other sections are 60, actually 64, 65, so a little bit higher than our section. Okay, so they have more students. So what does that mean? We had to try a little harder, eh? Yeah, it's a little competition there. So anyway, I will use a little bit of time if I have in the lecture, just quickly go over some of the question. Otherwise, you are welcome to come to my lecture to. Do you know how to do this? How do you mute it? Unbelievable. Yeah, he keeps asking. Okay, that's a little disruptive. Okay. You have your phone here in the library L317. You have your phone here in library 317. Okay, thank you. Everybody knows. Okay, so let's start the lecture here. We're going to start a new lecture on Lagrange multiplier. Okay. Okay, in previous lecture, what we talked about is the directional derivative. So we're actually going to make use of that knowledge on this new concept called the Lagrange multiplier. So let me write down maybe a directional derivative first. So we're going to use this formula, okay? Okay, so this is the directional derivative formula. Now, and also in the previous lecture, another topic we covered is about to find the minimum and the maximum for a given surface. So basically, if you have a surface given, okay, then what will be the local minimum, what will be the local maximum for a given surface? If this is a surface function here, apparently maybe you will find here's a local minimum, here's another local minimum, right? So that's basically regarding this mean and the max here. Okay. Now for this one here, okay, this one we have two theorems. Basically, we have first derivative test, we have a second derivative test, trying to find those critical points and trying to find basically whether they're minimum or maximum or even the saddle points, right? That's what we learned from previous lecture. So for this type of question, what I would call this is basically called unconstrained. So this is basically called unconstrained problem. So there's no constraint. You have a surface at here. Just go around the x, y, z axis. Okay, just go around it until you find the minimum, local minimum locations. So no constraint. You're free to change the location for the x and the y, right? So that's unconstrained. But there's another category of problem here. Basically, it's called a constrained problem here. So this is what we're going to talk about today. Okay. So the problem formulation basically here is we're looking for so-called the mean and the max for. Thank you. Yeah, you're welcome. It's for constrained problem. Okay. So what's constraint problem here? So let me write down this thing here. Maybe I'll illustrate this using a couple examples here. Okay. Yeah. So let me give you example here. Okay. So let's say suppose that you're using the summertime to build a new fence for your backyard at here. Okay. Yeah. So you're designing a new fence. So this is what you're going to do, and you have your backyard, and then you say, okay, I'm going to design a new fence with an area of 1,200 square meters. So you know that your backyard area is fixed to 1,200 square meters. And your backyard is, of course, going to be a rectangular type of backyard. Okay, so you're going to build a fence around this backyard here. So let's say you have your L at here and W at here, okay, for the dimensions of this backyard fence. Okay. Okay. So here is some of the material you decided here now. So here, let's say this is your front end of the backyard here. So for the red portion at here, okay, you decide to use a little more expensive material. So let's say you decided to use a $50 per meter, okay, for the material for this one end at here. And then for the other end, the other three ends, okay, so the other three sides, and you decide to use a little cheaper material, let's say $30 per meter. So that's the cost that you decided to spend on the 4 sides of this fence. Okay. So now the question here is, you have a total area 1200 meters square. You're not going to change that. So basically, that's the total area is fixed. But what you really want is, how can we minimize the cost? Okay, how can we minimize the cost? So that's a very typical question. Okay, if you're planning something at home, you may run into similar situations like this one, right? Yeah. Okay. So how do I formulate this problem here, right? How do I formulate this problem? Mathematically, to formulate this problem here, I guess first of all, okay, you want to minimize the cost, and then basically let's say how much cost, right, for this fence to be built. Okay. So let's say I'll call it cost. It's not cosine t, it's a cost. Okay. Cost basically relates to the length L and also this width W at here, and of course relates to the material for the sides, right? So you decided to use $50 per meter for these ends at here. So that basically means if there's L meter at here, then for this side here is 50 times L dollars. And the other 3 ends are all $30 per meter. So this is basically still L at here, so that's 30 times L for this side. That's how much it's going to cost. And then for these 2 sides at here, that's W. So 2 times W, and then times 50. Sorry, 30. Okay. So that's the total cost, right? That's the total cost at here. So a little bit of simplification in here. So you get 80L plus 60W. So total cost this much dollar. And you want to minimize this, right? So minimize this 80L plus 60W. Okay? Yeah. So the question here is essentially choose what value for the L and choose what value for the W will give you a minimum dollar value here. Okay? Yeah. So now, if you think about this, just this one expression, you're not going to go anywhere, right? Because there are 2 variables, and you can't actually just to come up with the answer for the L or for the W. Okay? So if you look at this question here, it does say the area of the fence. Okay? The area of the fence, no matter what L you choose, what W you choose, the area of the fence is always 1200 meters. So basically, you have an expression. So this area, okay, L times W will be always 1200 meters square. Okay? Yeah. That's quite big actually. So what you have at here is, this is basically, it's called constraint. Okay, it's basically constraint here. So your L and the W cannot be chosen arbitrarily, right? So if you have here, literally you can choose LW, but then you have this one here. You cannot choose an LW arbitrarily. Your LW has to satisfy this L times W equal to 1200. So that's called a constraint at here. Okay, that's called constraint. So this kind of question, basically, you're saying we want to minimize this and the subject to this condition, LW equal to 1200. Okay. So that's one type of question. That's the one type of question we want to solve for today here. Okay. So I'll formulate this more formally, and then I'll give you another example. Then we'll probably come back to this one here. Okay. Yeah. So. You know what? Let's solve this question first. Let's try to solve this question, and then I'll lay down the formal formulation. So I'm not teaching you the Lagrange multiplier yet, but if I give you this kind of question, let's say, what will be your approach to solve this kind of a minimization problem here? Would you have any idea? Yes.
You can put W in terms of L, substitute in the first equation, take further, set that equal to 0, and then find L.
Perfect, right? Yeah. So that's what you learned basically substitution, and then use the derivative first single variable to solve for the minimization problem here, right? Yeah. So excellent. So maybe let's just give a quick try it here. So here's a quick solution. So if I let L equal to 1200 over W, okay, so from the constraint, and then substitute into the cost equal to 80L plus 60W. Let's just call it C probably. Let's call it C here. Okay? C equal to D. So then you get C equal to 80 times 1200 divided by W plus 60 times W. And then we simplify this here. So the W at the bottom here. So 80 times 1200 and plus 60 times W squared. Okay, so your cost equal to this now. So now your cost, originally it's a function two variables, and now the function, it becomes function of a single variables now, right? Yeah, function single variable. It's essentially like y equal to f of x now, right? Okay, so now you can see, okay, if I want to find a minimum location, so we do a first derivative test. So set the dc over dw equal to 0. Okay, yeah. So let the derivative equal to 0. Now this one here, you need a quotient rule to calculate this derivative here. There are a lot of big numbers at here, so I'm gonna just let a, okay, equal to that big number, and then b equal to this big number here. Okay, just to simplify the writing a little bit. So a equal to 80 times 1200, b equal to 60. Good. Okay, so then take the first order derivative, and the first order derivative you end up with basically bw squared minus a over w squared, and you let it equal to 0. Okay. So the solution in here give us w equal to positive negative a over b. Okay. So you set this equal to 0, basically just the numerator equal to 0, and then that give you w equal to this solution. So w takes either positive or negative, but this is about a fence you're designing, so you're not going to take the negative. So basically you only take the positive value. So then you substitute a value here. A is 80 times 1200, b is 60, a little bit simplification, then you end up with 40. So w equal to 40. And then L, applied it here, so that basically L will equal to 30. Okay? So actually the width is a little bit longer than the length. So that give you the solution. If you build that length and that width, and you will have the minimum cost. And how much cost would that be? Substitute the two values into the cost function in here. You get how much dollar you're going to need, right? Yeah. Okay. So that's an approach that you will use. Okay. Before we learn this so-called Lagrange multiplier here. Okay. So, but I'll give you a different approach. Okay. Give you a different approach. But you can imagine now, actually, here is a constraint LW equal to 1200. So this is actually still okay. You can use a substitution in here. So what if the constraint actually is so complicated? You know, it's a square root L squared plus W squared. You know, if your constraint is very sophisticated constraint, then substitution probably not going to be able to be used to solve this type of question here, right? Yeah. So that's basically the idea. We want to find a more general solution, say here. So here's a formulation. More formulation of the problem. Okay. So more formulation of the problem here is objective is either maximize or minimize, okay, a function z equal to f of xy. Yes. Is that good? Yeah. So you want to minimize, maximize a function. So I'm going to use the function two variables to illustrate here. Okay. Yeah. Now, if I stop writing at it here, then you're basically looking at is the unconstrained problem. Then you do a first derivative, you do a second derivative test to find the minimized and the maximized location or the values, right? But now we have basically a second line in here. So subject to, so let's see, we have a constraint at here, and the constraint is basically it's a subject to subject to a function, to a constraint g of xy equal to c. C is a constant. Okay. So that's the typical formulation for this type of constraint problem. Okay. Across the board, you have a function trying to minimize or maximize, and at the same time you have a constraint for the x and y to stick to. Okay. So xy is not arbitrarily going in the xy plane. It has to be on this curve at here, right? So essentially, this one here, this is a curve. Okay, this is a curve. So g of xy equal to constant always give you a curve. Good. Okay. Okay. So another example. A very good example for this kind of constraint here, very well known, is it's called the milkmaid problem. Okay, it's called milkmaid problem. Anybody ever heard of this problem before? Okay. No? Yeah. So basically, the problem states is you have a river at here. Okay. You have a river, okay. And then you have basically a milkmaid at here with a bucket. Okay. So her location is at this location at here, current location. So the task for the milkmaid is basically to rinse the bucket in the river and then go to the next cow to get the milk. Okay. So let's say the next location of the cow is over here. So basically now, let's suppose that there's something urgent happening, that the milkmaid has to finish the work as quick as possible, right? So the idea essentially, she needs to go to the river, rinse the bucket, and then go to the cow here. So how could she finish this as soon as possible? So the only way is what? To find. Exactly, right? To find the shorter distance. So basically, you go from here to the river and then come over here to find the shorter distance. Okay, but this is a moving point here, right? This can be changed, not a fixed. So basically, the question here is, where would that point is to give you the shorter distance here? Okay. Yeah. So let's see if I denote this as a point P, right? If the current location for the milkmaid is, let's say, xm, ym, and the cow location is xc, yc. So these two locations, we know them already. And then this is your location for the position P at here, okay? For the position P. So now the formulation in the problem basically is to minimize the shorter distance. What distance is this? The distance basically it's a distance equal to PM plus PC, right? So PM plus PC is the distance. And mathematically, if I have the coordinates of the two locations, and I have the point P location, which we will try to find out here. So that basically give you x minus xm squared plus y minus ym squared, then plus x minus xc squared plus y minus yc squared. That's the distance. That's a general distance, right? Even without the river, you pick any point in the plane, and that will give a distance P and PC like this. Good. However, the point P is not an arbitrary point. The point P has to be along the bank of the river at here. So if suppose that the river here has a mathematical curve given by g of xy equal to c, okay, then the question in here is you're trying to minimize the distance but subject to a certain river curvature type of a function here. Yes? Oh yes. Yeah, thank you. Good. So that's another example for constraint problem in here, right? Constraint problem. Good? Yeah. Okay, so enough of this formulation. So now you can understand now basically what are we talking about here, right? Constraint problem here. So I will try to derive basically a formula here by introducing the so-called concept of Lagrange multiplier to provide a generic solution to this type of problem here. Okay. Yeah. Okay. So next, let's talk about Lagrange multiplier. Okay, so I'll use a very generic question here to illustrate. So objective here is related to a surface z equal to f of xy. Now, in most of the cases that we're going to dealing with, we're going to deal with the minimization problem. Okay, and so we're going to minimize this function in here, okay, and then subject to the constraint g of xy equal to c. So that's the question in here, right? Okay. So let me draw some curve here to illustrate this problem. So here's z equal to f of xy. Okay. I will just draw some arbitrary surface here. Okay. Okay, so this is z equal to f of xy here. Good. At the same time, you have a constraint here. So the constraint is g of xy equal to c. Now, so let's draw an arbitrary curve. Okay. So let's say this is g of xy equal to c. So that's a curve. This is basically your constraint here. Right, it's a constraint. So I want you to imagine basically what's happening here, right? Okay. So suppose that you are going to basically go along this constraint g of xy equal to c. Okay. Yeah, so basically you're not going anywhere. The xy value will always be on this curve g of xy equal to c, right? Yeah, so there will be basically a person at here, okay, walking around this curve at here. Now imagine while this person, okay, let's call it B at here. If this person is gonna go along this curve C, then at the same time, right? At the same time, that corresponding xy fitting to the surface f of xy, you're gonna get a point on the surface, right? You're gonna get a point on the surface. So as it's moving along the curve, and guess what happened to this person? Let's say A at here. So the A will eventually happen to trace out what? To trace out another curve on this surface at here. Does that make sense? Okay. So if you move the B along the curve C, then you're gonna get a curve A, okay, moving along this surface z equal to f of xy. So now basically the question here is, if you want to minimize this one here subject to this, basically what are we looking for now? We're looking for what? We're looking for basically the locations along this traced out curve at here, right? So apparently in this case the way I draw, okay, so there will be a minimum here, there will be a minimum in here, the local minimums. Does that make sense? Right? So ultimately this kind of a constraint problem here, right, can be formulated in a much more simpler case. What's the minimum for the trace out curve at here? Okay, and that's essentially the solution, right? So you're looking at this solution, you're looking at this solution here. Okay. So I'll give you a simple example. Maybe let's say, for example, let's say z equal to x squared plus y squared, and we can draw this easily, and that's a paraboloid type of a surface. Okay. Yeah. Okay. So now imagine this, right? Let's say if I'm going to go along the x-axis direction in a straight line. Okay. So this is your constraint at here. Maybe maybe this constraint here, maybe y equal to 2. Who knows, right? Is that good? Yeah. And this is actually one of the assignments you're doing for this week at here, basically. So if you go along this y equal to 2 like this, and guess what type of curve will trace out on this surface z equal to x squared plus y squared? If you go along here, what type of curve will be traced out on this surface? Yeah, right? That's a parabola basically to trace out. So ultimately what you do is you can substitute y back into this formula here. So you got a z equal to x squared plus 4, right? So basically you will get a curve, okay, will look like this. And that's, you can imagine, visualize by, there's a plane. That plane essentially goes through this straight line, and if you use the plane to cut through this surface, you get this parabola type of curve. And this curve right here is a z equal to x squared plus 2 plus 4. Right, so that's the curve here. That makes sense? Okay. So once you have the curve, you can immediately see, so where is the minimum? The minimum is right here, right? That's the minimum here. And the minimum probably somewhere on the xy plane. So if you choose a completely different trajectory, okay, or a constraint, then you will trace out a different, basically, different curve on the surface. Okay? So like the drawing I have it here. That makes sense, right? Okay. So now if you understand this process now, so let's lay down a few other things, and then we'll find the formula now. Okay? Yeah. So let's go back to this general formulation here. Okay, the general formulation. Yeah. So you have a surface and you have a constraint. Now I want you to change your perspective to the curve slightly. Okay, to the curve. So we're talking about this as a curve. So this one here is a curve. But I want you for now, just temporarily, consider this g of xy equal to c, okay, is actually considered as a level curve for w equal to g of xy. Okay, so just temporarily, where is this curve from? Right, this g of xy, and that you can absolutely think it of as a level curve for this function w equal to g of xy, right? So when you have a w equal to gx, you let the w equal to c, then you get a level curve, isn't it? Right? Okay, it's a level curve. Like this case here. So you have a y equal to 2. That's basically a plane for this plane at here. Okay. And if this is a special one, so wherever you want to slice it, you end up with that curve. y equal to 2. Okay, so that's the first thing I want you to think of here now. Okay, if this curve here is part of a level curve for this guy here, and now if you recall that, okay, if I'm going to take the gradient del g, okay, so you have a function w equal to g of x, y, right? And then I can take the gradient vector del g, isn't it? Okay, I can take the gradient vector del g. Is that all right? Yeah. So I can take, you can always get a del g here. Now, next thing I wanted to do is I want to use a unit vector u hat to represent the direction of moving. Is that all right? So I have u hat, okay, representing basically the direction along the curve g of xy equal to c. Okay. Okay, so time to jog your mind now. When we learn the gradient vectors, what is the relationship between the gradient vector and the level curve? So you have a function g of xy here. You take the gradient vector, and then you also at the same time you have this as a level curve g of xy equal to c. What's the relationship between this gradient vector and the level curve? Or what is the relationship between the gradient vector now and the u hat basically? Right? Perpendicular. So this gradient vector, right? Gradient vector is always perpendicular to the level curve. Or in other words, the gradient vector is always perpendicular to the tangent of this level curve. Is that good? That's a fact. Okay, there's no argument there. I don't need to prove this. I proved this some lectures before. So you have a curve here. You take the gradient vector. For example, let's say if I take the gradient vector over here, so I would be able to generate the gradient vector, and these two will always be perpendicular. Okay, will always be perpendicular here. Okay, so this is your fact number one, right? This is the number one fact. Get it here. I have another fact, and together we'll be able to get the Lagrange multiplier. Okay, so now let's look at the second fact. Okay, the second fact here. So second fact is this. Second fact is to do with the directional derivative now. If you're going along the direction of u hat, so there is a traced out curve here, right? There's a curve. So the person B go along the direction u hat, then the person A will what? Will either go down or go up, isn't it? Right? Okay. So the person A, the question here you probably ask is, how fast does this person A will go down or will go up as this person B is moving in the direction of u hat? What's that concept? That's the concept basically is the directional derivative, right? Directional derivative. So it's like this one here. If you're moving this way here and it's going down and up, okay, and what will be the rate of a change for this curve here? Right? What will be the rate of a change for this curve? And that's given by the directional derivative, right? Directional derivative. So the second fact comes from the directional derivative. Directional derivative formula is this. Okay? Yeah. And what this formula basically gives us is, it's the rate of a change. Okay, it's the rate of a change for what? For this curve, right? For this curve traced out on the surface. when there is a change in u hat direction. Okay, that's what directional derivative basically means. You move along that u hat direction, and how fast will it go up or down, right? For this curve at here. So that's what the directional derivative basically will tell you. Does that make sense? Okay. So look at this simple example. Look at this simple one here, right? Look at this simple one here. So apparently over here, that directional derivative will be probably a negative, and then it'll be probably a positive, right? Okay, as you're moving along here. So tell me, what about this location? What will be the value of the directional derivative at this location? It's 0, isn't it, right? Because at that location, there's no change, because it's basically look at the curve at here. That slope at that curve, that location, is 0. Okay, so essentially this is a slope concept, right? It's a slope concept. Sometimes positive, sometimes negative, and sometimes it's 0. Okay, so this df over ds equal to 0. Now that's the important information that we want to check it out, right? Yeah. So this equal to 0 basically means when this equal to 0, okay, at that location, no change, okay, in f there. Okay, there's no change in f. That equal to 0 basically is telling us, okay, so that location, right? This location at here, or this location at here, is a critical point. Okay, it's either minimum or maximum. It's going to be a critical point because the slope at that location is equal to 0. Is that good? Yeah. Okay. So, and what does directional derivative equal to 0 mean, right? So if you look at the formula for the directional derivative, we actually looked at this before in the previous lecture. So if this equal to 0, basically means your grading vector dot u hat equal to 0, and dot product equal to 0 basically means the two vectors must be perpendicular to each other, right? Perpendicular to each other. So that basically means del f perpendicular to u hat at a critical location. Okay, at a critical location. Now this is basically the number 2 fact. Okay, does that make sense? Okay. So now look at number 1 fact and number 2 fact together. So what's the fact number 1 again? Fact number 1 is del G perpendicular to the u hat, right? Yeah. Del G is always perpendicular to u hat. And then del F will be perpendicular to u hat if that location is a critical location, okay, for the trace out curve. So if you look at these two conditions here, first of all, grading operation always give you a vector. So this is del F is a vector, this del G is a vector here, right? So both of them are going to be a vector here. So where's the del F? So we don't know what our del F is, but it probably will change its direction. But at the different location, del F will point into a different directions, right? Okay. But at this, let's say, at this critical location, so you have a del G at here, you have the u hat at here, and at the same time, what's the other fact 2? Fact 2 is del F is what? Del F is also perpendicular to the u hat, isn't it, right? So I draw the del F this way. Maybe it's also that way, but that's okay, right? So now you look at this drawing at here. When two vectors are perpendicular to the same vector, basically means that two vectors must be what? No. When two vectors are perpendicular to the same vector in the same plane, they must be parallel, right? So they must be parallel. So this basically telling us that del F perpendicular to the del G. Now this is not true all the time, right? This is only true that this is parallel to this at critical location. Okay. So at the critical location, you have two vectors, two greeting vectors, perpendicular to each other. And that's not good enough. We want to formulate this one into a mathematical expression, right? So what's the nature when two vectors are parallel to each other? If you have two vectors are parallel to each other, what's the nature of it? The dot product is zero. Mathematically, they are just what difference? Just a multiple difference, right? A multiple difference basically means you can use a scale between these two vectors. So we introduce a parameter lambda here to indicate that scale. For ease of writing future, I'll put a negative here, so negative lambda here. Now this lambda here is basically called Lagrange multiplier. Okay. So at the critical location, the two greeting vectors are parallel to each other, and you can express or connect the two parallel vectors using a scale or using the so-called Lagrange multiplier, right? Yeah. And yes.
Why did you put the negative there?
It really, actually, you don't have to, but it's just a sort of a convention or formality. Yeah. Because later we're gonna move this term to the other side here, so the negative is going to become a positive. Yeah. But mathematically, really doesn't matter, because you put a negative here. In the end, when you calculate lambda, you probably end up with a 3, or if you don't have a negative, then it's just negative 3, right? So that's the difference. Okay. So ultimately, from here is the way that we can calculate our critical locations and also find out the mean or maximum values here. Okay. Yeah. So let's see what happens at here, right? Let's say expanding these terms here and then to give us the necessary conditions for us to be able to find a solution. So del F equal to negative lambda times del G. Greeting vector, basically, what is it? It's the partial F over partial X, partial F over partial Y, right? And that equal to negative lambda times partial G over partial X, and then partial G over partial Y. And that's directly from this expression right here. Okay. Okay. So move this term slightly around. So you have two vectors equal to each other. Basically means the components of the vector must be the same as each other, right? So that basically telling us partial F over partial X, okay, equal to negative lambda partial G over partial X. Partial F over partial Y equal to negative lambda partial G over partial Y. Okay, so move everything to one side. Okay. So that single expression will give us two equations, right? Two equations right here. So this is basically equation 1, equation 2, okay, from this equality. So now you can visualize if you have your function f, you have your function g, you can calculate the partial derivatives, and you can plug it into it here. Okay. Basically, you get how many variables now? You got x and y, and also what? variable lambda, right? So 2 equations, 3 variables. That's not good, right? We need one more equation in order to solve the 3 variables here. What's the third equation? Exactly, beautiful. So you have your constraint here, right, to make use of. So these 3 equations, okay, these 3 equations will be able to solve, give you a solution for x, y, and the lambda. And that's basically the idea for Lagrange multiplier here for the original formulation of the problem, constraint problem here. So I'll give you examples how to solve this, but in terms of the formula, here's the formula, right? And that's it. Okay. So before I give you an example here, there's a little bit variations in terms of the Lagrange multiplier here. Okay. So there's another variation in here is basically what probably you will see is it's like this. So we define a different function. We define a function. Let's say x, y, lambda. So let's define a function L, and this is defined as f of x, y plus lambda g of x, y minus c. Good? Yeah. So define this one here. Now this one here, there's a name associated with this. This is called Lagrangian. Okay? This is called the Lagrangian in here. Now you probably will see, well, okay, so this is quite complicated now. But I'll formulate the problem here now is, if I give you this function of 3 variables, okay, I'll give you the function 3 variables, and then if I ask you a question here is, can you find the critical point for this function L? Okay, so how would you do? Can you find the critical point for the function L? If I give you a function 2 variables, what would you do? If it's a function 2 variable like we learned in the previous lecture, if I give you a function 2 variable f of x, y, how would you find the critical point? Derivative test, right? A derivative test basically means what? You're setting which to 0? First order, that you're setting the gradient to be 0, right? Yeah. So when gradient equal to 0, basically you're at this critical point, right? So let's see here. If I say what's the min or max for L, so what would you do? You basically set the gradient to be 0, right? You set it equal to 0. Let's check it out. What does this gradient L equal to 0 give us here? So gradient equal to 0 basically means partial L over partial x equal to 0, partial L over partial y equal to 0, and the partial L over partial lambda equal to 0. Okay? Yeah. So what does the first equation give us? So let's look at the L. Here's L at here. Okay? Here's L. What does the first equation give us? It's 0 equal to, what is the partial L over partial x? You have 2 terms at here. So the first one becomes partial f over partial x. And then you have this term at here, right? You have this term. Lambda is a constant. Lambda is not a function of x at here. So the only function is x is over here. So that basically you got what? Lambda times partial g over partial x. Okay. Second one, you get partial f over partial y, lambda partial g over partial y. And what's the last one here? 0 equal to what? When taking partial L over partial lambda, this is not a lambda function. The only one here is lambda, but then you treat the whole thing at here as a constant. The coefficient is constant. So you end up with g of x, y minus c equal to 0. Okay? Yeah. So this is what happens if you take the gradient L, okay, the gradient vector for the L, and set equal to 0. Now if you look at these three equations here, now what's the three equations? What are the three equations we just derived? That's exactly the three equations 1, 2, 3 we just wrote it down, isn't it? Right? That's exactly the same equation. Okay? Yeah. So these three equations here is exactly the same equation as the other one there. Okay. But what is the point of doing this then? So you see the point here is these three equations is derived based on this what type of problem? Derived based on this so-called constraint problem, right? But these three equations is derived based on what type of problem? Unconstrained now. That makes sense, right? So here you don't have any constraint. You're just trying to find the mean or max for the L here, right? Yeah. So that's the idea of defining a Lagrangian in here. Especially if you go into optimization area, and you'll see this quite often in here, defining a Lagrangian, and then before moving on and calculate the minimum or maximum locations, right? Yeah. But in our case, really, in terms of formula, we need to remember it's essentially the three formulas here. That's the equation here. Or, technically speaking, just one plus constraint. Okay? Yeah. That's basically what you need to remember. Good? Yeah. Okay. So, let's look at a couple of examples here. Okay? So this is the first question in here. Find the minimum value for this function subject to this constraint in here. Okay? Yeah. And I used this function already. This is a paraboloid, and subject to a constraint y minus x equal to 2, which is a straight line, right? It's a straight line here. Okay. And I do have an animation in here just to illustrate. We'll come back to this a little bit again, but this is the y equal to z equal to x squared plus y squared, the paraboloid, and then the bottom dot is the straight line y minus x equal to 2. So it's like basically you go along this straight line here and watch that red dot on the surface. Then it will trace out basically a curve, right? It will trace out a curve right here. Okay. And finding the minimum here basically means you're finding at the location somewhere over here, right? Okay. Yeah. Now another thing is you might ask is how come we're so confident what we're going to find is actually a mean? Why am I not saying you find a max for this one here, subject to the constraint, right? Because why? There's no rigorous proof here. Because the function given at it here, what's the nature here? It's a surface and it's pointing west, up, right? Yeah. So this is typically what we call a convex type of function. Yeah. And that's why. And we just see this is basically it's going to be a minimum here. Okay, yeah, that's a tree sum. Okay, so let's use the method that we learned just now and to solve this question in here, right? Yeah. Basically, we are looking at here. This is your function f. This is your g here. You're looking at these three equations, right? The three equations that are here. Yeah. So let's take what's the first one? Partial. Basically, the first one is partial f over partial x plus lambda partial g over partial x equal to 0. So partial f over here is 2x and then plus lambda times partial g over partial x, which is -1, so equal to 0. So this is your first equation. Second one, partial f over partial y. Okay, so this will end up with a 2y plus lambda times 1 equal to 0. So that's two equations. And the last one here, you write down this constraint in here, which is y minus x equal to 2. So 1, 2, 3 equations. Okay, and then you can start to solve for x, y, lambda. This one is actually not bad. This is a set of linear equations, so you actually will be able to solve this using a very typical substitution in here. And then you see the next one. Often in time you end up with nonlinear equations. So there's no set rules for solving a set of nonlinear equations. But substitution most of the time will work, but actually may not work sometimes. Okay. So let's say in this case here, from number 1, I can derive lambda equal to 2x. Right. So this is number 1 here, and then I can substitute this lambda equal to 2x into equation 2. So we'll end up with 2y plus 2x equal to 0. So together with the last one, and then we can solve for x and y. So we end up with x equal to 1, y equal to negative. Sorry, x equal to -1, y equal to 1. Okay. So from here you get this much, and lambda is equal to -2. Okay. -2. Good. So here is the critical location at -1, 1 location, and you can calculate basically the minimum value at this location, so which is at -1, 1 location. So plugging into original function, okay, which is 2. So that's the optimal solution. So you have a 1, 1, -1, and optimum value is minimum value is 2. Okay. Okay. So so there's nothing really to show here. Another one I'll show you a little bit a different perspective. So let's take a look at another example. Okay. All right. So in this example here, I'm going to choose the same. Okay. I'm going to choose the same function. Minimize the same function in here, but I'm going to change the constraint. So this time I'm going to change constraint. Okay, so g of xy equal to xy equal to 3. Good. Okay. Okay. So, and I want you to give a few minutes, see if you can just to use this formula here, see if you can work out something yourself. Okay. But to give you a little bit better idea what's going on in here, so this is essentially an animation in here. Constraint is xy equal to 3. So you have basically it's a parabola curve right here, so xy equal to 3. Okay. There are actually two curves, right? So one is in the first quadrant, the other in the third quadrant for xy equal to 3. So only draw the one in here. Okay. Now, if you walk around that curve, okay, if you walk around that curve, so then it will trace out another curve on this surface at here. Okay, so that's how it look like. And of course, in this particular case, we're trying to find that location, right? Trying to find that location, okay, by making use of the Lagrangian concept right here. Okay, so yeah, give you a few minutes here. Let's see if you can work it out, right? Yeah. Okay, anybody has any luck getting an answer out of here? for this question? Anybody? Oh, yeah. What do you get? No, there's a student behind you. Yeah. Yeah, that's right. Yeah. Root 3 is, which one is C or X? X the location equal to root 3. Yeah. Very good. So, let's try it together here, okay? Yeah. So we have partial f over partial x plus lambda partial g over partial y equal to 0. So that gave us 2x plus lambda times x equal to 0. Partial f over partial y lambda, this is x here, partial y equal to 0. So this is y here. So 2y lambda x equal to 0. So 1, 2, 3. Okay, so 1, 2, 3 equation. In the lecture notes, I'll give you two different type of solutions. The first type of solution, usually substitution should work, and this one works for this question here. What we do is from equation 1, we can write the lambda as this, and then sub into equation 2. Okay, so we're going to get 2y minus 2x over y times x equal to 0. Okay, so this one here give us x squared equal to y squared. Okay. Yes, negative. Sorry. Yeah. Good. So sub into number 2. Oh, I kept the negative here, and then you get x squared equal to y squared. Okay, so this is somewhere you're gonna have to be careful now. When x squared equal to y squared, what it happens is it could be x equal to y or x equal to negative y, right? So it could be either one of these cases here. Okay, but not always you have to use both of the solution in here. As often in time, one of them is actually it's not valid. Okay, so for example, if you look at this one here. If you look at the x equal to negative y, so x equal to negative y gives what? If you put it into a third equation, you'll get negative y squared equal to 3, right? So you're going to get this. And that's impossible. So negative y squared will never be able to be 3, unless y is a complex number, but that's not what we're talking about here, right? Yeah. So basically, only the x equal to y, okay, is what we're going to take. And once you get x equal to y, and then substitute into equation 3, so now we get x squared equal to 3, or x equal to positive and negative root 3. Now this is somewhere you're going to have to keep both, okay? You're going to have to keep both of the negative and positive sign in here. Because what you're going to have to do is, so for x equal to root 3, you'll get y equal to root 3. And for x equal to negative root 3, and y is negative root 3. Okay. So that's basically there are two locations. Two locations will give you a critical point. Okay, critical point. So both will give us minimum value, and you can calculate the minimum value by substitute into original function, and both will end up with the same critical value, number 6. Okay, valued at 6. Okay, that's this another one. So to change to a different, basically, constraint here, you get slightly different value here. So lambda in this case, you'll be able to get which is equal to 2. Okay. Yeah. Okay. So now you get the idea Lagrange multiplier to solve this constraint problem. It's actually not too bad. Okay, following the procedure and formulating the problem often in time also takes a little bit of time here. So now I'll show you a little bit of animation at it here. Okay. Okay, so remember there are two solutions, right? There are two solutions because there are two curves. When you draw the, if you draw the xy equal to 3, you get two curves. Okay, yeah. So I only sketched one at here. So if you're going along here, I want you to watch the blue color and the red color vectors. Can I have your attention? Sorry, there's still a few minutes to let you go, okay? Watch the two vectors, the blue color and the red color. So the red color here, okay, is the grading vector for xy equal to 3. You see the red color is always perpendicular to this xy equal to 3 curve. The blue color is the grading vector perpendicular to the original function f of xy equal to xy squared. Okay? So you see that point is the moving point on the surface. And what happened when the point is at the minimum location? The del g and the del f, what happened? They are becoming parallel, right? Become parallel here. And also look at that circle. What's this circle here? This circle is the so-called what? The level curves for x squared plus y squared, right? So look at the curve at here. Basically, as you're moving here, see the blue color is level curve. At the critical location, the level curve and the constraint becomes what? Tangent, right? Become tangent. Okay? Yeah. So the nature of this constraint problem here, okay? It's basically, this is a very good illustration for the relationship between all the vectors and the level curves. Okay? Yeah. Any questions? Okay. Okay. So as I said, the midterm, if you require assistance, come to my office. Okay. I'll be willing to go over with you guys.